Welcome back to the World Model Podcast. In today's episode, we'll be discussing the debugging crisis. How do you find a bug in an AI's reality? When a traditional software program fails, we have debuggers. We can step through the code, inspect variables, and find the faulty line. But how do you debug a world model? When its internal simulation of reality goes haywire, when it predicts that a car can drive through a solid wall, or that a beneficial drug will be toxic, there is no simple line of code to blame. The error is distributed across billions of parameters in a high-dimensional latent space. Today, we delve into the emerging crucial field of interpretability and debugging for generative world models, the hunt for bugs in a mind's eye. The problem is one of opacity and scale. A world model's understanding of is encoded in its latent space, a compressed abstract representation. When it makes a bad prediction, we need to ask, what is the flawed concept in its latent space? Did it learn a wrong association? Does its physics module have a blind spot? Traditional probes are useless. We need new tools. The first class of tools involves latent space traversal and visualization. Researchers use techniques like TSNEA or UMAP to project the high-dimensional latent space into 2D or 3D, trying to find clusters and boundaries. They can then take a latent vector representing a normal scene and slowly nudge it in a certain direction, watching as the decoded output morphs. Does moving in direction X always make scenes darker? Does direction Y introduce physical impossibilities? This can help map the organization and the corrupt regions of the AI's conceptual map. The second, more powerful approach is counterfactual probing. You ask the model, given this scene, what would it look like if the law of gravity was slightly stronger? Or, show me what must be different in this image for the car to be upside down. By analyzing how the model manipulates the latent space to answer these what-if questions, you can infer its understanding of causal relationships. If its counterfactuals are physically nonsensical, you found a bug in its causal model. The third frontier is automated consistency checking. This involves building a secondary system of hard-coded logic or a simpler, more interpretable overseer model that checks the world model's output for basic physical, logical, or semantic consistency. If the world model generates an image of a person holding 5 bananas in one hand, the checker flags it as probable failure of grasping or counting concepts. But the ultimate challenge is the way we may be debugging a reality that is different from ours, but internally consistent. The AI's world model might have discovered a valid but non-intuitive shortcut or representation. The bug might be in our expectation, not its prediction. This makes debugging a dialogue, not an inspection. My controversial take is that the ability to debug world models will become the most critical and rarest skill in the AI industry of the 2030s. It will require a hybrid mindset, part computer scientist, part cognitive psychologist, part philosopher. These AI reality debuggers will be the high priests of the new age, the only ones who can peer into the minds we've created and fix the hallucinations. Without this capability, deploying powerful world models in safety critical domains such as medicine, transportation, or military is an act of reckless faith. Debugging isn't a niche engineering task. It is the essential safeguard for a world run by simulations. This brings us to our final episode of the season. After 28 deep dives into the architecture, application, ethics, and limits of world models, it is time to synthesize, to weave all these threads into a single narrative about what this all means for our species. This has been the World Model Podcast. We build the tools to understand the tools. Subscribe now.